Hello and welcome to Day 2 Notes of AP Calculus Unit 1 on Limits. We're going to go through the Day 2, so if you're following along within the notes packet or the Day 2 packet, today's goals are just going to be to talk more about limits today, how to evaluate and find limits. We're going to be discussing tips and tricks with those indeterminates. So if you remember, the major indeterminate form we've discussed so far is that 0 over 0. Is it undefined? Is it 0? Is it 1? We don't know. It's an indeterminate. We cannot determine what that means. So we're going to be talking a little bit about those today, as well as getting into some properties of limits and those kind of things. But to get our brain going, I thought we would look at a little bit of a graphical review. So what I would like you guys to do is just pause the video, as per usual, as usual being in the second time I've ever done this. Go ahead and pause this video to try these 9 limits, and then I'm going to add to them as well. I want you to not only find those 9 limits. Oh, you know what? I think it's on your paper. You're also going to give me the actual value of the function for each of these. So we're going to do these 12. So take a second, pause the video, try them, and then I'll go over them real fast. So pause. Okay, welcome back. And if you didn't pause, now it sounds really goofy. The limit as x approaches from negative 3 from the left. So remember that little negative after the number means from that direction or from the negative side. So if I look at x equals negative 3 and I follow along the function from the left-hand side, getting close, I look like I'm approaching a height of 2. From the right, going towards negative 3, it looks like if I follow the road map, it looks like I'm going to a height of 5. Because the left side limit and the right side limit are two different values, the general limit does not exist. And then f of negative 3 is the actual value. So if I look at negative 3 to see if it's defined or not, it has a closed circle and 5, so the actual value of the function there at negative 3 is 5. Okay, if I look at 2 now, this is where I'm headed. From the left, I'm going to a height of 7. From the right, I'm going to a height of 7. That means if the left limit is 7 and the right limit 7, the general limit is 7. And if I look for the defined value, going up x equals 2, it doesn't look like there's a defined value anywhere. So I'm going to actually say that the actual value at 2 does not exist. Remember, the limit is not the same thing as the actual height of the function or value of the function. It's the intended height. So that's the big difference between a point and a limit. Okay, so now 7. Here's where I'm headed on the x-axis. So following from the left, I'm heading towards a height of 4. From the right, I'm heading towards a height of 4, which means the limit would be approaching 4. But the actual value at 7 is 3. Okay, so the limit and the actual value, the intended value and the actual value are different there. Okay, so now that we got our brains going, we're going to get into some special functions that the AP exam really loves to give. And it's not one of the families of functions that we kind of talk about in Math 4. In Math 4, we stuck to the basics. Linear functions, quadratics, exponentials, logs, the trig graphs, and all of those. But there are absolute value, square root function, all of those. But there are three other ones really that the AP exam loves to give that they just expect you to know what it looks like. So we're going to go over 2 of those 3 today and then also do some limits with them, just because we should practice limits. So the first function we're going to look at is f of x equals absolute value of x over x. I like to call this like the step stool function. You'll see why in a second. You could also see it as x over absolute value of x. Either way, it could be fine. These functions are going to take the same transformation rules that all of our functions did. What's nice is that as long as you know your parent and your transformation rules, you can really graph any function in existence. So we're going to learn the parent here, but then any transformation rule can also work. So what I'm going to do to get started here is I'm just going to look at this graph and I'm just going to plug in points. When in doubt, just keep plugging in points until you can get a general idea of what the shape looks like. So if I plug in negative 5, the absolute value of negative 5 is 5, divided by negative 5 is going to give me negative 1. So at negative 5, I have the point negative 1. Now, honestly, we should be plugging in a lot of points and not just integers, but I'm going to be lazy here and I'm going to plug in some integers. So -4, the absolute value of -4 is just 4. And I'll kind of write down what I'm doing. So -5, I ended up getting out -1. If I plug in -4, I get 4 over -4, which is -1. Oh, look, if I plug in -3, absolute value of -3 is 3 over -3 gives me -1. If I plug in -2, I get out -1. If I plug in -1, I get out -1. If I were to plug in any of these decimals, I would get out -1. So I can see this is a horizontal line. Now, if I plug in -0.5, I would get 0.5 divided by -0.5, and that gives me -1. So even -0.1 would give me -1. But guys, look what happens when I plug in 0. I get absolute value over 0 over 0. That's an indeterminate. I have no idea what's happening in the graph there. So what I can say is that up on the negative side, until I get really, really close to 0, it's going to be -1. So I'm just going to do an open circle there to represent that. Now, if I look at the right-hand side here, if I plug in something like 5, I end up with a +1 because 5 divided by 5 is 1. 4 divided by 4 is 1. 3 divided by 3, 2, 1, 0.5, 0.1. It's always going to give me 1. But again, as soon as I get close to 0, I end up with an undefined spot in the graph. So I end up getting a graph that looks like this. I call it the step stool. It's like 2 baby steps, and that's it. So let's answer some limit questions. The limit as x approaches 0 from the left, well, if I head towards 0 from the left, the function is -1. If I head towards 0 from the right, the function has a height of +1, which means the general limit does not exist. So this is what we call our step stool function, absolute value of x over x. Now, another point that I want to make about this function is the following. So I'm just going to erase my little table here. Absolute value is really a piecewise function. And we're going to talk a little bit more about piecewise functions today and how we deal with them. But if I think about absolute value of x is really -x when x's are less than 0, and x when x is greater than or equal to. But because we have it over x, I'm going to exclude 0 from the domain because we saw it already doesn't work because x you can't divide by 0. So if I were to rewrite this as a piecewise function and simplify each piece, it would just be -1 and 1. Which is what I ended up graphing. But now you can kind of see it in its piecewise form. So if I were to put like a 2 out here, that would vertically stretch it. It would just be -2 and 2. If there was a 0.5, it would be at 0.5. It's just a little like 2 flat lines coming together. And then we can transform that function either way. So that's one of the functions that they love this graph. It's like one where I'm going to be like, you're going to have at the front of your notebook, a random resource page of all these like random things that come up throughout the year that college professors are just assuming that you know from some point. You might have learned it for 15 minutes one day 3 years ago, and they're like, but you should know it because they're college professors and they just think you remember everything about mathematics because they do, which is just incredibly not fair. So as we go through this, because this is going to be taught like a college class, if we come to something and I'm like, you should know this, and you're like, dang, I don't know this, I would keep like a little like cheat sheet in the front of your notebook or in the front of on like a nice like highlighter yellow color piece of paper of just all these random facts that you can kind of just keep putting down, and it creates like a nice cheat sheet. Now, can you use that cheat sheet? No, but it's like a reference page for you as you go through your life in this class that will kind of help you out. So step stool graph is the first one. Let's go to this function, which is actually known as a step function. It looks like this. In your book, they don't use the symbol here. You'll also see this function written like this. So I'm just going to write it right underneath it. It'll sometimes look like this, or it looks like this, okay, in command form. So this function is what's known as the floor function or the integer function. So what it says is it's finding for whatever input you give it, the output is always going to be an integer. So it's going to say, what is the greatest integer that is less than or equal to the number that's put in as the input? I like to call this the round down function, because like no matter what you're trying to figure out, you're going to be able to round this down to the nearest integer. So to give you an idea of how this works, I'm just going to make a little table under here and just pick some random points. I'm going to start on the positive side because I feel like it's going to be easier for you to understand. So if I plug in 0 into the integer function, what the integer function is saying is, what is the largest function that is less than or the largest integer that is less than or equal to that number? Well, the largest integer less than or equal to 0 is 0. So we would have the point 0, 0. Now, if I were to plug in something like 0.5, I'm saying what integer is less than or equal to 0.5? 0. If I were to plug in 0.9, what greatest integer is less than or equal to 0.9? Still 0. So that's why I call it the round down function. Like if I were looking at a number line between 0 and 1, it's saying always like what integer is just to the left of whatever you're doing. So all of these would just round down to 0. So we end up with this graph that always has an output of 0. And even if I was going to do 0.99999, it's still going to be 0. So I'm going to get close to 1, but I'm going to draw an open circle because that represents that 0.9999. But as soon as I plug in 1, guys, the greatest integer that is less than or equal to 1 is 1. So all of a sudden this function jumps, and at 1 it has a point of 1, and it's going to stay at 1 until I hit 2, and then 3, and then 4. Now the negative sides get a little tricky, but I always think round down or round to the left, or like on a number line, you're always going left. So if I were to plug in -1, it would obviously be -1. But if I were to plug in -0.5, which is right here on the number line, the greatest integer that's less than or equal to -0.5 is -1. So you're still rounding down to the integer. So the left side of it would just kind of look like this. I'm trying to draw these open circles, y'all. I'm failing and talking into the void of nobody. There we go. That's better. So this is why this is called the step function, because it legit just looks like a bunch of steps. Okay, where the left side of each step is closed and the right side of each step is open. If we were going to be talking about the domain of this function is all real numbers, so -infinity to infinity. The range of this function is all integers. Now, I'm not going to write that. I'm just going to write this in set notation because it'd be easier. So if you remember set notation, the set of y such that y is an integer. So I'm going to say y is in the integers. A little fancy Z with that double staff. All this math knowledge from domain and range. You probably did most things in interval notations, but sometimes inequality or set notation is helpful. This is one where I do it. This one, if I go back to my step stool, the domain here is all numbers except for 0. So I would say x is an all real number, except x can't equal 0. Or you could do like -infinity to infinity. My range is just the set -1 or 1, because that's the only two outputs. All right, now that we have these two basics graphed down, let's do a quick little limit problem. So if I go towards -1 from the left, so here's my -1 from the left, it's -2. From the right, it's -1, which means the general limit does not exist. So both of these have limits that exist in a lot of places, except where these little jumps happen. Those are going to be places where the limit does not exist, okay? And those are two functions that you're going to see a lot, and I just want you to be familiar. You can actually graph this in your TI-84. There is an integer command. I believe it's under math. I'm going to write it down so that you can discover it on your own. And then if you go over to number, it's number 5. It says INT. So if you graph it just in your graphing thing, you would just do int x and then graph it, and it'll give you little steps. Now it's going to look like the steps are closed on both sides because of the pixelation of your graphing calculator. Know that in your graphing calculator, they're not going to show you these open circles, so you have to know where the open circles are. That's part of where you are smarter than your calculator, okay? Okay, so moving on, I'm going to take a little sip. Moving on, I want to kind of focus on limits with piecewise functions for a minute, because piecewise functions can be tricky, especially in the side where a domain breaks and it is non-inclusive, okay? So piecewise functions, remember, are different functions over different domains. So you can see this first function, f of x, is a linear function with a slope of 2 for x's that are greater than or equal to 0, and a quadratic or parabolic function here that's been shifted up 1 for everything less than 0. Now, if you can picture these graphs, I know that a line is a continuous function, and I know a parabola is a continuous function. That means like the limit is going to exist at all of those places in that graph everywhere. The only place where it may not exist is where the domain breaks at 0. So if I wanted to figure out if the limit existed at the break in the domain, you have to go to the heart of when a limit exists. So last class, we learned a limit exists if and only if the limit from the left of a function is equal to the limit from the right of a function. So if I were doing a proof, a mathematical proof here, I'm going to say, I'm going to calculate the limit as x approaches 0 from the left of f of x, and the limit as x approaches 0 from the right of f of x. And then I'm going to find each of those limits to determine, does the limit in general exist? And then for funsies, let's just actually find the actual value, because again, the limit and the actual value are two different things. It's just that 90% of the time they end up being the same thing. Okay, so if I wanted to find the limit as x approaches 0 from the left of this piecewise function, I'm going to look at my domain and see which function contains the left of 0, which is going to be that second function where x is less than 0. So what I'm going to do is, even though this domain doesn't include 0, I'm going to find the intended height of that piece at 0. I just know if I was graphing it that intended piece would be an open circle, since the domain doesn't include 0, but we're still going for the intended height. So I'm actually just going to plug 0, not like negative 0.1 or something close to 0. I'm going to plug in 0 to find what would the height of this function be if 0 was included. Okay, so I'm plugging in 0, and I get out a value of 1, which tells me as I'm approaching from the left-hand side, this graph's height is approaching a height of 1. Now from the right-hand side, I'm going to go to the domain that's to the right of 0. And again, I'm finding the intended height at 0, so I'm going to plug 0 into that function, and I get negative 9. Now I can conclude then, because the left-hand limit does not equal the right-hand limit, the general limit does not exist. So I'm actually going to cross out the equal sign because that doesn't make sense grammatically, I mean. Judgment-free zone. Remember, this is always a judgment-free zone. Okay. And if I was doing this on an AP exam, so here's your first thing. If I wanted to do this, I would say the limit, this would be like my justification. The limit as x approaches 0 of f of x. Remember, if you don't put that f of x after the limit command, you've written nonsense, and they will give you no credit for that. So that's just my warning to you. I'm going to grade you like an AP exam. So I will be real petty and picky sometimes when it comes to notation, because we have to give the notation some respect in its integrity, because it's actually it's mathematical sentences, okay? So it has to make sense mathematically, and if they're going to take off points, we're going to take off points, because bad habits we're going to break early. So we would say does not exist, and you can use DNE for does not exist. That's common math language, because I'm going to be a little... The limit as x approaches 0. Man, I wish my pen would write from the left does not equal the limit as x approaches 0 from the right of f of x. And that's your first mathematical proof you guys have ever done. So no 2-column proofs or paragraph proofs or flow charts or anything you did in Math 2. Ours are just going to be statements and reasons. Now for fun, if I were to ask you what f of 0 was, you'd have to look at which side includes 0, which is the right side. So if I plugged 0 into the side that included, the actual value is at -1. So graphically what's happening here is I have a parabola that's been shifted up. There's an open circle. And then that's supposed to be an open circle. Oh my gosh, I just can't even, guys. And then a closed circle at -9. So it looks something like that. So I have a jump there, even though it's impossible to tell because that open circle just will not. Let's try it one more time. I'm a perfectionist at heart. There we go. Just make it bigger. Okay. So we end up with something that kind of looks like that. So you can see that the left side and the right side don't look the same. Now, if we look at the second one, I want you to look at this domain here, because what we have is we have a function and the domain is x cannot equal 2. And then we have the second line of this function where it says 4 at x equals 2. This graphically represents just a point. That's saying when x is exactly 2, the height or value of that function is exactly 4. So I have the point 24 on this graph. Okay, this means the domain is everything except for 2. So if we're talking about limits, the limit exists if the limit from the left and the limit from the right are the same. And because this function is on the left of 2 and on the right of 2 at the same time, it's coming from both directions automatically. So as long as this limit exists in the first one, then the limit at x equals, we can say the limit is at x equals 2 exists as long as if I substituted 2 in and I got a real number, then we can say that the limit exists. So to do this one, I'm going to take the limit as x approaches 2. And again, because it's a two-sided domain here, it's everything except for 2. I don't have to do 2 from the left and 2 from the right. I'm just going to do 2. Now to find the limit, I'm not going to say the limit is 4 because the point is 4. This is the actual height, okay? And the actual height is not the same as the intended height. The function, we're approaching 2, so we have to think is what parts are at 1.999 and 2.001. Like that's the function I want to use. So I'm going to plug 2 into that expression to see what I get. Uh-oh, team. If we look what we get, I end up with 0 over 0. Does that mean the limit does not exist? Dramatic pause. No, it means we need to do some work, okay? So when you get 0 over 0, you just don't say, oh, the limit doesn't exist, okay? 0 over 0 means, oh, I got to do something to see if it exists. So what I'm going to do is I'm going to take my function, and like we did last time, I'm going to take that expression and I'm going to factor it. Now I'm going to look at my factored form and ask myself, can I simplify it? And the answer is yes. These x minus 2 expressions would factor. So really all I'm finding is the limit as x approaches 2 of the expression x plus 2. Which now, if I substitute in algebraically, I end up with 2 plus 2. Notice that I'm replacing the x, so the limit goes. And I end up with 4. So does the limit exist? Yes, the limit exists because when I did the limit, I got a real number. And since it's a real number, it's got to exist. Now, if I look, my limit is 4 because that's everything around 2. The actual height is 4. That's not always going to happen. It just happens that in this function, there was a hole at 4. And so what they did is they plugged the hole and filled it in with a point. But this doesn't, you never look at this, guys. Only ever look at what the limit is, which is everything around 2 or approaching 2, not what actually happens at 2. Okay, so on that note, what I kind of want to spend some time on is how to do indeterminate problems. So what I'm going to recommend for you, as usual, try these problems on your own. So pause this video, try these problems on your own, unpause it to see the solution to see if you're right. So it's kind of like you're doing your own exit ticket, okay? You're doing a problem to try, and then we'll check your answer with me through the video. Okay, so in this first one, the limit as x approaches -3 of this expression, the first thing I'm going to do is plug in -3. So if I plug in -3, I end up with 9 minus 3 minus 6 over -3 plus 3. Now I have to show that that limit is 0 over 0. Does that mean it does not exist? No, it means I need to do work. So what I'm going to do is I'm, again, going to try to factor this. So factoring is my go-to. So if I factor that expression, notice that as I'm factoring that expression, I rewrote the expression and I brought my limit command down, okay? Because I haven't actually found the limit yet, that command needs to stay in my notation until I actually plug it in. So I can see here that when I factor it, I get a common factor of x plus 3. So I'm going to simplify the expression. And now the expression that I have left is x minus 2. So now if I find this limit, I'm going to plug in -3. Notice at that step, at the substitution step, the limit command is gone again because I'm actually calculating the limit by plugging in the number. And I end up with a limit of -5. All right, so if we look at example 5, and you're asking yourself, how would I solve this problem? Well, I'm going to start by plugging in 0, which gives me 1/4 minus 1/4 over 0, which is 0 over 0. You knew that was coming because the whole section is called indeterminate practice, right? But what we're going to do here is talk about how would we simplify this. So think on your own, what are some strategies that you would do here to try to simplify or rewrite the expression. So that's your goal when you have an indeterminate, is you're trying to rewrite the expression or simplify it. Now I can see here that I have a nice little complex fraction. I have fractions within fractions. So my strategy is going to be to simplify this complex fraction. So to do that, this is a little review from chapter P, section 6 from last year. I'm going to get the common denominator between x plus 4 and 4, which is just those two unique factors together. It's not like I can just add x to the second fraction to make them the same. You can only do multiplication. So I'm going to multiply the first. Actually, I'm going to do a totally different strategy. I'm going to knock your socks off. This is the Miss Seitz way, and I love this way. So the common denominator is 4 times x plus 4. So I'm going to multiply the top and bottom by that same expression. And that's legal because that's just equivalent to 1. Okay. Notice I brought down my limit command. I wasn't lazy. And now look what happens. On the bottom, I end up with 4x times x plus 4. And I'm going to leave it factored because I'm going to have to like cancel or simplify something. But now if I distribute this in, if I distribute this to the first term, the x plus 4s are going to cancel, and I'm left with 1 times 4, which is 4. In the second time, when I distribute it in here, the 4s would cancel, and that would leave me with 1 times x plus 4. So now what I'm going to do is I'm going to clean up my numerator. Be very, very, very careful here because I have to distribute that negative in. So I have 4 minus x minus 4 over 4x times x plus 4. I can see if I simplify that these 4s are going to cancel. And I want to make sure I simplify this expression and reduce this expression as much as I can. Because even at this step, if I were to plug in 0, I get 0 on top and 0 on bottom. But if I reduce this by canceling out that common factor, now I end up with a -1 on top and 4 times x plus 4 on bottom. So once I've cleaned up and simplified my expression as much as I can, now I'm going to take my limit. And notice every time I rewrote my expression, I kept that command in front until I actually substitute the 0 in. And once that step happens, then you can drop that limit notation. So if you see here, once I do that, I end up with negative 1 over 4 times 4, which is just negative 1/16. And that would be the limit. So does the limit exist? Yeah, because I got this nice number. Sometimes once you simplify it, you're going to see that you're going to get like a number divided by 0, and that just means the limit doesn't exist. Okay, so looking at this one, if I plug in 0, I can already see that I'm going to end up with 18 minus 18 over 3 minus 3. Now this should also look familiar to you because we did it last class. This kind of looks like that little h situation. It looks like we're trying to find a speed of something or an instantaneous rate of change of something. Notice that we have this little limit expression in the front. So what I'm going to do to help myself through this one is I'm just going to actually distribute this out. So I'm going to go ahead and square that binomial using the square double square trick, minus 18 over, and then I'm going to simplify the bottom because I see those 3's cancel into h. I'm going to go ahead and distribute that 2 in. Now some of you guys could have done that in one step. Some of you would have to write that 3 plus h twice and then do it. We're all at different algebraic comfortabilities, so just be comfortable with where you're at, okay? This is not a speed contest when it comes to calculus. It's not if you can skip the most steps, you're the smartest. It's everybody is just got to do it the way they're comfortable, okay? So I can see the 18s are there, and then what I'm going to do is I can see I have 12h plus 2h squared. I'm actually just going to pull out the h. Even though I could pull out 2h, I'm just going to pull out the h because I want these h's to cancel. So now my limit problem is taking the limit of 12 plus 2h. That's the simplified expression. So if I take the limit by plugging in 2 or 0 for h, I end up with 12. So that would be the limit there. So again, every time I rewrote or did something algebraic to the expression, that limit as h goes to 0, limit as h goes to 0, every single time until I simplified it completely. And then once that h became the number 0, that's when you can drop the limit notation because you're actually doing the command by plugging in the number. All right, so that's the first part of it. What I want to kind of focus on for the next few minutes is just talking about different properties of limits and then like applying those properties so that if you know a basic limit, you can actually find limits of combinations of functions. So if I know a limit as x approaches 1 of one function and the limit as x approaches a different function at 1, and I know those limits, I can combine those two functions in different ways and actually calculate the limits of the combinations. And a lot of it, you're just going to kind of think about like the transformations. If you can make sense of it, then that kind of helps. So for instance, let's say the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x, a different function g of x is M. Now notice that this is both at x approaches c. It's at the same x value. Without that same x value, it doesn't make a difference. If I were to find the limit as x approaches c of the combination of f of x plus g of x, that limit would just be the limit of f of x plus the limit of g of x. So it would just be L plus M. If I subtract the two functions and find the limit of the subtracted functions, it's just going to be the subtraction of the two limits. Now this is a vertical stretch. So think about vertically stretching a function by a factor of k. If I had a normal function f of x and then I stretched it, it's just going to make it k times higher. So what we're going to do here is this would be the same thing as multiplying the limit as x approaches c of f of x times that coefficient k, that vertical stretch. This is called a constant multiple. In calculus, a lot of times we use the word constant multiple as opposed to the word coefficient, and I have no idea why. I'll be honest there, and why we teach you the word coefficient if then we drop it and you call everything a constant multiple. It seems a little silly to me. But the constant multiple here, we're saying k is a real number or a constant, so it would just be k times L. Likewise, if I wanted to multiply two functions together and graph that function, the limit as x approaches c would just be L times M. If I divided the two functions, it would be L divided by M, except We have to have an extra constraint that m can't equal 0 since we're not allowed to divide by 0. And if I wanted to like raise a function to a power, we would just take the limit and raise it to the power. The reason why I made it a fractional exponent is just because it applies to roots. And so understanding that like square root of f of x is the same thing as f to the 1/2. And then it kind of makes it applicable in all those situations. Okay, so here's your moment to check. I want you to try these problems. Again, pause, try these problems, and then unpause, and I'll be going over the answers. So pause. This is a good time to pause right now because I'm taking a sip of water anyway. Okay, so for this first one, notice that I have g of x at x approaches 3. So I have the function g of x, which I know the limit is -2, and the limit of f of x at 3 is 4. Now this is the limit of g of x plus 1. You can think that means that g of x graph was shifted up 1, or you can think about this as the limit as x approaches 3 of g of x plus the limit as x approaches 3 of 1. Well, g of x we know is -2. Now, the function 1, that's y equals 1. Guys, y equals 1 is just a horizontal line at a height of 1. Every limit would be 1 because all the heights are the same. So we would just add 1 and get -1. All right, constant multiple rule here. If I want the limit as x approaches 3 of 5 times f of x, I'm just going to do 5 times the limit of f of x, which is 4. That gives me 20. 2 times f of x would be 2 times 4 minus 3 times -2 would be my limit. So that gives me 8 plus 6, which is 14. If I wanted to find the limit as x approaches 3 of f of x times g of x, I'm just going to do 4 times -2 and get -8. If I wanted to take the limit as x approaches 3 of the square root of f of x, it's just going to be the square root of 4, which is 2. Now, I want to make a point here that confuses a lot of students. It's not plus or minus 2. If the square root is already in the expression to begin, then it's not a plus or minus situation. It's the principal square root. It's whatever sign is in the square root is the sign of your answer. So if this was a negative, then you would have to say it's -2. But because it's just the square root, we're going to assume it's the positive. The only time you get a plus or minus is when you are in the process of solving an equation and you need to add a square root into that process to find solutions, okay? So if I had x squared equals 4, I am now solving an equation and I'm taking this and adding a square root to both sides of that equation and getting that plus or minus situation, okay? This is an evaluation. We are just evaluating or calculating a limit. This is not solving anything. So we are not doing a plus or minus, okay? So g of x divided by f of x is just going to be -2 divided by 4 is -1/2. So all these little nuances about mathematics, you're going to really start to like see them and understand them. All the math you've ever done is being put together in this beautiful class. And it brings all these different facets of mathematics together, and you start to learn different things with a high level of integrity and really understanding numbers and their senses, which is why, many reasons, this is one of my favorite classes to teach. Okay, so number 8. This is a trickier one. So if we're going to be doing this one, I want you to pause and I want you to try this problem for approximately 5 minutes. Try whatever you can get, do whatever you can for 5 minutes, then unpause this question. There's lots of different ways to attack this problem, and I'm going to show you one way, but I want to see like one of the steps, or if any of the steps, like things that you try to do to solve this question. So pause it, try it, see what you can do, and then I'm going to show you what I do with this question. In typical class, you guys would just present the answers, but yeah, COVID learning. So here we go. So pause it, try it, unpause it, and we're ready to go. So now with a question like this, if I plug in 0, I end up with 0 plus 0 over 0. That's an indeterminate. So now I'm going to try to do. Now, the only things that we've done so far are factoring and simplifying complex fractions. We haven't done any other strategies, and this problem is going to take some other strategies and use some of the properties that we did to kind of talk about how to find this limit. So one thing I'm going to notice is that this expression is a fraction with a monomial on bottom. So when I say monomial, I mean one term on bottom, and it kind of makes a heart shape. I say this a lot in class, and you'll learn this. If it looks like a heart, one strategy you can do is distribute the division or break the heart. Okay, so you can always break a fraction that looks like this, like a heart, but if it was reversed, like a butt, you cannot break a butt, guys. You can only break hearts. So we're going to say x approaches 0, and then I'm going to break this into 2x over x plus sine of 2x over x. Now, one common mistake I see with this problem is that people think that they can pull out the 2x or factor it out. This 2x after the sign is part of the angle of the object of that command sign. You cannot pull out of that angle, guys. So it's illegal to factor that, but we can split it. And what I see here is if I simplify it, I end up with 2 plus sine of 2x over x. So now this one I can see as a sum. I could just find the limit. This limit is 2. So this limit right here I know is just a constant, it's 2. But the question here is, what do I do with sine of 2x? So one thing I'm going to do is break this up so that it's 2 separate limit problems. Okay. Now this limit I know is 2. But this limit, I still get 0 over 0 when I plug in 0. So I need to think about what else I can do here. So now what I'm going to try to do is I'm going to use an identity. And since it's sine of 2x, maybe I'll try the double angle identity. So there's another strategy. 2 sine x cosine x over x. Now you're like, I don't know how this helps me. I'm just trying anything. And that's what I'm going to say. Just try till you get stuck. We'll go through the homework. We'll take some time going over the homework. So if you get stuck, you'll be able to fix your mistakes. And that way, you know, you have that to kind of go through. Last class, during our virtual class, we looked at a function sine of x over x. So just to recap what we did in class, we looked at sine of x over x, which kind of looks like this, and the limit of this is 1. So now what I can see here is that I have this sine of x over x combination of factors within this limit. So what I'm going to do is I'm going to rewrite the second one, the second expression, as 2 over 1 times sine of x over x times cosine x. And my computer is being really slow, so I'm going to have to try to write this. And that's legal. Notice that when I broke up the factors, only one of these factors got the x, because if I put these back together, I'd have to do top times top times top, which would give me, and bottom times bottom times bottom. So 1 times x times 1 is x, but if you made it like x, 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 then you would have x cubed. So with multiplication and addition, just make sure you're really comfortable on your rules here. So what I can do is I can just take the limit of each piece of this second part. So if I look at here and I want to take the limit of 2 is just 2 times, now I'm treating this as a product, just like that f times g situation. Now if I look at this function on its own, the limit of sine of x over x as x approaches 0 is 1. So I know the limit of that function is 1. And then the limit of cosine of x over 1 would just be cosine of 0, which is also 1. So when I evaluate each piece of the limit using the properties, I end up with 2, which was the limit from the first part, plus 2, which is now the limit of this product together, which gives me a limit of 4. That is like the hardest example I could possibly give you, because it took, look at all the different things we had to do here. We split the fraction up, we had to use a trig identity to rewrite it, and then we had to look for functions that we were comfortable with to rewrite it as a product of functions where one of them was something that we knew. Okay, so that's like a really, really hard example for you to look at. But just to kind of go over some tricks for indeterminates, factor is always a good one to use. I would say combined fractions. I'm going to say split fractions. And then in parentheses, I'm going to say like hearts. Okay. We can use identities. We can look for limits we know, like that sine of x over x. Okay, so look for limits we know. We could also, another strategy that we didn't talk about was using a conjugate. Conjugates are used with radical expressions, so I'll give you an example. So if I had 2 minus root x, the conjugate would be 2 plus root x. So just multiplying that to get rid of radicals. I think that's it. Now the other strategy I want to say to you is graph on a calculator or on Desmos. If you can look at the graph, especially if it's a calculator active question or a question you're allowed to use a calculator on, that's always my go-to strategy. So those are some strategies. Now you might have other ones you can add to this list. We'll talk about probably more during the virtual class, but for now, that's all we have. So on that note, that is the end of the day. I hope you have a good one, and I will see you